It's a pleasure and a privilege to have Maria Kanakidu. I had printed a page, but I forgot, of course, because she was the recipient of the Wilhelm Bjerknes Prize in the European Geophysical Union a couple of years ago, 2016. Mm-hmm. I was trying to put that because I think it's a more objective thing that I could do. Of course, I have a long-term relationship with Maria since I was a PhD student and she was a postdoc working with Paul Crutzen in Mainz, mm-hmm. One of the Max Plancks in Germany. So we have known each other for many years, and I'm probably biased to say that she's an outstanding scientist. And in addition to that, a very nice person. Some of you have already got the chance to verify yourselves that part, and the scientific part also to some extent. But the Bjerknes Prize is sort of a more objective way to put it, and there they give her this prize for the outstanding science, the leadership in terms of promoting new subjects and new scientific questions. All the chemistry you see nowadays in current models, she started it. To our dismay, I must say, at the beginning, when chemistry was very simple, was the oxidation of carbon monoxide and methane, and that formed ozone at the global scale. Well, she put many complex things that we had to learn about time, and now that's the standard for current models. She has also worked in aerosols and deposition, influencing biogeochemical cycles. So it's not only atmospheric chemistry, but also biogeochemical cycles and the interactions from the atmosphere and the land with the ocean, and that's also a new field. And this one, which is the topic of today, is also one of the new fields in which she has been a leader and changing a bit the paradigms of how the organics play a role in terms of cloud condensation nuclei. So, with no further ado, I introduce to you Professor Maria Kanakidu from the University of Heraklion in Greece, who I will be lucky enough to visit next year and continue the work we have already started here. She has been here for a few weeks, and 2 papers are coming out of it.
Not on cloud condensation nuclei, however.
Not on cloud condensation nuclei, okay. But another stuff that's very interesting over the Pacific. So, thank you, Maria, and the floor is all yours.
Yeah, thank you very much, Laura. Thank you for coming here. I was expecting an empty amphitheater, but it's not. It's a pleasure for me to be here, and I will miss you because I'm going next week back. And so I decided to talk about recent work we have done on cloud condensation nuclei, where a lot of people participated. So what do we care? Why do we care? That's the first question. And we know that in the recent IPCC, the 2013, a new one is coming soon, we can see the importance of atmospheric composition for Earth's climate. The right side, you see something you should know, that Earth is warmed up by the sun. If we don't have the sun, then energy is not enough to keep the atmosphere of Earth at plus 15 degrees that is actually. And even if we have the Earth there, if we have the sun there, then if we don't have the atmosphere with the components that are into it, then we're still cold. That means we will have minus 18 degrees C. And because we have those greenhouse gases that absorb outgoing radiation from the surface, then they capture this radiation into the atmosphere. We have a greenhouse effect that is warming the atmosphere to what is the actual state, which is plus 33 degrees Celsius. compared to the minus 18 degrees that we would have without the atmosphere, and this is the reason that we live on Earth. Otherwise, life would not have been possible. And however, humans have changed this equilibrium between what comes in and what goes out at the top of the atmosphere. And the change in this energy coming in to energy coming out, that means to this balance, is what in the IPCC reports they call radiative forcing. And this is relative to 1750. And on this slide, whatever is to the right is warming the atmosphere, and whatever is to the left is cooling the atmosphere. So we have carbon dioxide that everybody knows about, the major greenhouse gas that is warming, but we have also a number of other components that are warming the atmosphere, like methane, which is a chemically active species, halogens, and tropospheric ozone, and N2O, and also we have other chemicals, carbon monoxide, non-methane, volatile organic compounds, and nitrogen oxides that are chemically reactive, and they're forming ozone, they're affecting methane lifetime and methane levels in the atmosphere, so indirectly they affect the climate. And this is what we see in here, the important role of chemistry for the Earth's climate. It's very interesting to go a bit further and look on the importance of aerosols. Here we do have the aerosols and their precursor molecules, from where they come from. And we can see here aerosols that are warming, like the black carbon coming from fires, and the aerosols that are cooling the system. And this is this is part of the direct effect of aerosols. That means the interaction of aerosol itself with the radiation directly. But we also have here the cloud indirect effect. The aerosol indirect effect that has to do with the changes that the aerosols can imply to clouds. They can make clouds. They can make them more dense. They can make them rain more often or evaporate more often. So they change the whole hydrological cycle. And if we look at the right side here, this is the level of confidence. How well do we know that this is happening, and how well we quantify it, how well we can predict it in the future by climate modeling. And you can see that among all those things, this part, those interactions of aerosol with clouds are the lowest in knowledge. So we really have the largest uncertainties in climate change simulations are associated with these aerosol cloud interactions. That's why this work is important. But what are those aerosols? I don't know how many are chemists here and or physicists, but quite a lot. But it's always good to know that atmospheric aerosols have various sources. They can have anthropogenic sources coming out from cars, exhaust from chimneys of industries and power plants and shipping, for instance. But you can have airplanes that are missing here. But you can have also natural sources, volcanic eruptions, dust, fires, and sea spray. So you experience all of it every day. But what is coming to the atmosphere, we call it aerosol, but it's not really exactly the same thing. On this picture, you can see soot from biomass burning. You can see pollen, a lot of allergy for humans associated with pollen. You can see bacteria that are flying in the air, and they are very important. You can see the mold that it's also existing in the atmosphere. And smelters, you have also mining and smelter issues here, minerals, pollen again, and viruses. So those are some of the particles that have different shapes, different sizes, and different properties. So they have different sources also. We said, let's get it a bit again. What happens? We have anthropogenic sources. We have natural sources. Fires is in between. You have human-induced fires, and you also have natural fires. And the natural fires take into account that climate is changing, going to a warmer. We're going to a warmer climate. We might have more fires in the future. So those, and we have also vegetation emissions. So the emissions from vegetation and from fires, for instance, are climate-driven sources. And same is for the sea spray, because it's wind-driven, and extreme winds are more often now expected in the future. Then once you have all those aerosols, but not only aerosols, also in precursor molecules of aerosols, like organic gases that can form organic aerosols, or sulfur dioxide emissions, which is a gas, but then it makes sulfate aerosol. So once they are emitted, we have the particles that exist in the atmosphere, or primary from the emissions directly, or secondary from chemical formation. They can interact with light. This is the direct effect we have seen. They can also interact with the water in the atmosphere and affect the cloud properties. They can act as cloud condensation nuclei, affecting the warm clouds, or as ice nuclei, some of them, which make ice clouds. So we have both. So it's very interesting to understand how this system works. And obviously the other part is that those are deposited onto the surface, and then we get into the biogeochemical cycles that Laura mentioned before. And they can bring nutrients to the environment. So we said that they can be formed also in the atmosphere by chemistry. So if you have sulfur dioxide in the atmosphere, then this is oxidized to sulfuric acid. Sulfuric acid has very low volatility, so it can make clusters. And clusters in the atmosphere can also occur when you have very low volatility organic compounds. And those can grow by condensation of more gases onto the clusters, or by coagulation between them. And they can keep increasing. Mainly this increase is found to be dominated by organics in the environment. That means the first cluster is by sulfuric acid with organics, but then the growth is the organics that are producing it. And they can increase sizes, 3 nanometers, 50, 100 nanometers. Then it gets a cloud condensation nuclei. It's big enough to get to absorb water from the atmosphere and grow to make it to cloud there. Obviously, some of them they can be lost by coagulation or pre-existing aerosols, so they don't add new CCNs, but they do exist as mass into the atmosphere. And this review paper evaluated that the cluster formation from CCN number concentration can increase the CCN number concentration by a factor of 2 to 9. So I have forgotten to get my time. So we'll be okay. And this part is the one that we are more interested in, because it's where the uncertainty with aerosol clouds interaction exists. So going back to the roots for the aerosol of different properties, we see that they can be solid or liquid. They can have different physical properties, chemical properties, different chemical composition, and they can have different optical properties. Some are absorbing, some are scattering, more or less scattering, and different hygroscopicity, and different volatility. And on this slide, you see how we classify them in terms of the particle dry diameter in nanometers. So we have the nucleation mode, the Aitken mode, which goes until 100 nanometers. Then the accumulation mode that goes to 1 micrometer, and the coarse particles. You will hear very often talking about PM1. PM1 means particulate matter that has a diameter, dry diameter, if it's dry, smaller or equal to 1 micrometer. PM2.5, same, but for 2.5 micrometers diameter. And PM10 with 10 micrometers. So if you look on this one, this slide from the EPA, you have a human hair, and you see the diameter is something like 70 micrometers. Here you see a fine beach sand, which has a diameter of 90 micrometers. And we talk about smaller than 10 micrometers, smaller than 2.5, those red spots in there, micrometers, and I think I don't have the PM1 on this figure, but it's even smaller. And this is what will affect climate. Just pay attention to that. Obviously, the smallest it is, easiest is getting into our respiration system. We breathe it, and then it brings all pollutants into our body, and it can even get into blood and the brain and produce different problems of health. So that was the size. Now I have to show you something from my own country. So we have a beautiful station. You are very welcome to come and visit it in the East Mediterranean, on Crete Island, where I'm coming from. And this is Greece. This is the whole Mediterranean. Italy, Spain. You already know Spain, France, etc. So we are down here, and this is our station. Now it's a bit better, but we measure since 1993 aerosols. And continuously since 2000, a good record of total aerosols. But I'll show you here is the ACSM measurements, aerosol mass spectrometer measurements in reality. And the PM1 aerosol composition at Finokalia. This is what I want to show you with that is we talk about aerosols, but they have a lot of stuff into that. Now it's not pollen and it's not a classification like pollen, smelter or whatever, or bacteria. Now you see the organic fraction in green, you see in black the black carbon, you see in red the sulfate, in yellow the ammonia and ammonium, and in blue a little bit of nitrate. A little bit of nitrate because it's PM1. It's a very small aerosol. Nitrate is mainly in larger particles. So we have a lot of different compounds there that have different hygroscopicity. And except the dry mass, we also have a lot of water that we generally call aerosol water. What does it mean? It means that you never have a very dry aerosol. Dry aerosol does not exist. It always has a little bit of water around it because there is water in the atmosphere. So on this slide you can see the diameter of an aerosol population because it's very difficult to measure one particle. In general, you look at distribution. You have a classroom, you have different people in, different sizes, different masses, different volume. So that's the way we also characterize aerosols. So on this slide you see the distribution with the diameter and the volume. This is the volume distribution, which is practically the mass distribution, because you have the density, you multiply volume by intensity, you get the mass out of it. So you can see you have this aerosol population at relative humidity 20%. Then you can say that it's dry, almost dry. But if you increase the relative humidity in this environment, then you get the blue line, which is 68% relative humidity, and you have another distribution of aerosol. What is in between? I was not very good at doing that, but it's the increase due to the water. So the aerosol is capturing water. And you can evidence this every day in your life. This is a very nice bridge. It's the best bridge we have in Greece. It connects Peloponnesus, which is a semi-island. It's not an island, it's connected to but it connects Peloponnesus from Patras, where Spiros Pandisia is working in Greece, to the main continent. It's earthquake resistant. Above, it makes it to 8.5 for sure. I don't know if it will make it to 9. For the moment, we did not experience higher than 7 something. So it's an earthquake resistant bridge, which is very nice. And if you have a 10 micrograms per cubic meter aerosol in the atmosphere, then you can see it from Spiros office. But if you get 50 micrograms per cubic meter, then it started getting hazy. This hazy is both the fact that you have aerosols and that these aerosols have a lot of water also. So, multiple scattering. It does not allow, the aerosols do not allow you the the light from the object to reach your eyes. It's going around. So this is exactly, in reality, what happens if you are the sun and you bring a light to the earth. It's aerosols are multiple scattering, and they are also making fog. So this is I don't know how I'll do it. This is a very nice slide that is from NASA's website, where you can let's see, can I have it? No. Where you can see the different aerosol types. It also says which one are what. So you can see the dust, how the dust outbreaks, how they follow the general circulation patterns. You have probably done a little bit of general circulation in here. So you see the westerlies in the mid and high latitudes. You see the trade winds in the tropics, like that here and like that there. So you see how the dust is blowing out from Sahara and from the Gobi Desert and the Arabian deserts there. Might have a little bit here, will come soon in red. From the Patagonia, you have some, the other desert you have also, and those are the fires. Mostly are the fires from the tropical forest, and that's the Patagonia stuff. And then you see the sea spray coming with the cyclonic system in the south, and white is the sulfate from sulfur dioxide. I don't know if we see volcanoes here, but
you see sulfate from
melting. Okay. So there might be some volcanic eruptions also somewhere if you look. But okay, that's a very nice video. You can find it on the website of NASA. And okay, let's finish that. So we continue. We have those aerosols, and what we care about now is how we go from the aerosol particles to the droplets. So that's a point. And so the CCN, the aerosol particles, we can talk, it's about the 0.1 micrometer diameter, roughly. They start from the 100 nanometers. Then to get to cloud droplet, you need a larger diameter, which is 10 micrometers, and then to go to, it's a radius, sorry. And then to go, this is caricature anyway, and then to go to the larger cloud droplets. And in the cloud droplets, then you get a radius of 50 micrometers. That means it keeps growing. You start from aerosol, teeny bitty, it goes to the CCN size. That means it's increasing the size, and then it goes to the cloud droplet number, cloud droplet concentration, and then it goes to droplet. And this is a kind of proportional sizes, and this is all huge stuff. Is the raindrop? Then it's heavy enough to drop. Has to be to grow to significant sizes. So let's go to our study now. That was the introduction. The aim of the study, what we have done in this European project is Bacchus, which was looking at the aerosol cloud interactions and try to integrate both the natural and anthropogenic aerosols. What we try to do is to evaluate the general circulation and global chemistry transport models that are able to simulate aerosols and cloud condensation nuclei. For their ability, see how good they simulate aerosol number concentration. You will see it as NA, number of aerosol. The cloud condensation nuclei, CCN, which is a fraction of the aerosol number, becomes CCN. Not all of them are growing. Like some of them, they can just they coagulate with others, and then they can be removed before growing to CCN. We have the cloud droplet number concentration. You will see it as CDNC, or sometimes I did not write it here, N number D, number of droplets. Yeah. And then we looked also on the long-term seasonal variability and the short-term dynamical behavior, if we can get the variability of the system. So a total of 15 global models have been run for the period 2010 to 2015, and we compared with observations at 8 European sites and 1 site in Japan, and those observations are surface observations. So what we've done is we asked to the models to provide PM1, particulate matter smaller than 1 micrometers, aerosol chemical composition, so how much sulfate, how much organics, how much black carbon, etc. We asked them also to provide distributions and numbers for the N3, number of aerosols with diameter smaller than 3 larger than 3 nanometers. That means you take the 3 nanometers and whatever exists above it. The N50 takes the 50 nanometers and whatever exists above it. N80, same, 80 nanometers and whatever above, which means the N120 is only a fraction of the N80, which is a fraction of N50 and which is a fraction of N3. Okay. So if I ask you which one will be the highest number, what you tell me? Exactly, it's the N3. Very good. So you got it. So then the other thing we asked was the CCN at supersaturation, different supersaturations. Mainly we focused on the 0.2% supersaturation. And we also asked, we wanted the different supersaturations to be able to calculate the cloud droplet number concentration, as I'll discuss later on. And we wanted to compare the models between them and the models with the observations, and also to produce what we call ensemble model results or multi-model median results that I will show you, which is a kind of the state-of-the-art of model knowledge at the moment. So this is the multi-model median results for the at surface, because we had a surface station. So this is annual median of all models for the N3 particles diameter larger than 3 nanometers. And indeed, the maximum scale goes to 10,608, and this is larger than N50, which goes to 8,000 something, and this is larger than the CCN, which goes to 3,500. So the understanding is correct that side. What we see on those slides, we see that we have a lot of small particles over the continents. We look this side, and those are reduced when we go to N50 and when we go to the CCN. The right side gives us the model diversity. We took the standard deviation to the mean this time as a kind of measure for the model diversity. And we see that models have a lot of problems in the polar regions. We knew that already, but we see it again. And we also have very large diversity, which is goes up to 3, for instance. This means that you have 3 standard deviations. The standard deviation can be 3 times the mean value, which is very big. Yeah, obviously, it's very big there. And we also see some differences, significant difference also over burning regions. Within 50, we have less diversity because already the models, let me tell you the story then about it. The models have differences in how they parameterize the nucleation of particles, the new particle formation. I saw you in the beginning, I said sulfuric acid and organics, then they have to grow, and this is the aerosol microphysics representation, let's say, in the model. So this nucleation is the new particle formation a new particle formation in the models is different from one model to the other. And the further analysis we have done shows that this is one point of uncertainty in the models. And the second thing that we have shown, and we'll see it a bit later on, is that also the emissions that are introduced as primary emissions of aerosols in the models, they need to account for the size distribution. And the size distribution, yes, obviously, because you have particles at different sizes. And the size distribution that is used in the model is very different. And for instance, we can see that carbonaceous aerosols are emitted, are assumed to be emitted in smaller sizes than are indeed emitted. So there are points there, and this makes the big difference between N3 and N50. And then going to the CCN, we can see that this diversity is reduced. So which means that the models are activating the particles. Fast on that because I'm over time, I think. Yeah? Here we see similar figures, but for the sulfate component in PM1, the organic aerosol, and the black carbon. So you see divergences, for instance, for the sulfate, again, you have in the oceanic regions, you have also in the Arctic, for the same reasons we discussed before, the nucleation part. We also see for the organic aerosol large divergence over the sea. This has to do with the marine source of organic aerosols and the way they represent it is represented in the models. Okay, and then we have also significant diversity in black carbon at different regions. I think this has to do mainly with the microphysics in the models, how they make the aerosols growing and being deposited. So I still have to understand this one. I was not prepared for this maximum. I have to check on it, but when we look at divergences, we also have to look on the absolute number. That's why it's important to have this one next to it. If you have zeros, then divergence of 3 doesn't matter. I mean, even if you have one more particle, this will make you a large divergence. So we have to focus on where the maxima are and where the differences have significance. So the second step, once you see the divergences of the model, is to see how they compare with observations. This is a little bit old slide, but doesn't matter. We have, those are the stations we have in Europe, and this is the one in Japan. And what I present you here is the sulfate concentration as a function of the year at 3 different stations. Hutiala is here, Mace Head here, and obviously I would not go without Finocallia on the map. And you see this figure shows the minimum and maximum of the central 2/3 model. It doesn't matter. We took out the outliers, and we focus on the central models. If you want to, I can explain you then how this was done. And then we looked at the geometric mean of the models in this figure, and we compared with the observations. Okay. So what we can say that more or less the models are getting the order of magnitude for sulfate. Yeah, they're doing pretty good, except in Hutiala. Hutiala is a little bit a strange place. It has a lot of organics, but it's also very close to the to the polar regions. So there are a lot of frontal activity, and it's not this is difficult to be captured by the model. So sulfate is pretty okay, I would say. Here is the organics. It's another way of seeing this one, this figure. And we again see that the organics are somehow underestimated by the models. You see all the spots are above the blue line, in particular in Finocallia, they're far away. This is not surprising because in the past we have done intercomparison exercises for organic aerosol models, and we know that models are underestimated, and we're still trying to find out how this can be improved. So the situation remains bad. And now the number concentration, this is a very messy figure, but because I have the greens and the red together. But let's focus on whatever is red. Forget the greens. So the red is the N50. Particles, that's why it's above. Particles with diameters larger than 50 nanometers. So we see the red line corresponds to the median of the models. This is another approach now of comparison. The dashed red line at the bottom and the top is the minimum and maximum of all models. We do not take outliers here. We have all of them. And we make median, and we make 25 and 75 quadriles. So you see that the observations, which are the spots here, are underestimated. Some models are capturing. They're inside the models. That's why I put the minimum and maximum. That means models are capturing it, but they are not always the same model that is good. And that's very embarrassing. So you don't know how to handle it. But conclusion out of this one is that somehow the general trend in the variability is captured by the models, but they are underestimated. So the same for the 120. And go to CCN now. In this one we see Finokalia station, and this is the Jungfraujoch. Finokalia is our station in Crete, which we know that air masses there are well mixed around because it's an area that receives pollution from everywhere, and it's sunny, and we have a cooking system, so it's old aerosol, it's aged aerosol. And Jungfraujoch is in Switzerland. It's a very, I have not been there, but it's at the top of a mountain. It's a very Okay, it's a free troposphere environment during winter, and during summer it gets the boundary layer goes up there. So the station has a very important difference, summer-winter difference due to boundary layer height. So we see in Finokalia, where we have the aged aerosol, the black spots here are the measurements of CCN at 0.2 supersaturation, so that we underestimate. All models overestimate the concentrations, and in Jungfraujoch, all models underestimate the concentration. So we have a discussion. We can discuss that compared with the ability of the models to simulate aged aerosol one side, and the ability of models to simulate boundary layer conditions the other side. So. Overall, however, if we take all the stations, because there are more stations and all models together, the normalized mean bias is about minus 37, which means a 40% underestimate, roughly, if you take the multi-model mean. So I want to put two more things on table. The first is the contribution of organics to cloud condensation nuclei. All my life modeling, I was doing organics, so I cannot escape not saying about it. This is a base case simulation of our model, the TM4 model that we use also with Laura here. And you can see the maxima over biomass burning and vegetation regions, and also anthropogenic regions, and in India and China, Southeast Asia, etc. And if you remove the organics now, organics are emitted by combustion quite a lot, which can be open fires or can be fossil fuel combustion. They can also be produced by secondary organic aerosol formation by the oxidation of organic in gas phase. Most of the organics in gas phase are coming from trees, it's vegetation. There is also anthropogenic organics in the gas phase. So if we remove all the organics of the model, we can see this is the same scale, all the red is gone. There's something remaining here. India and China, and also in Europe, there's something in the US, but mainly what remains has to do with the inorganic part of aerosols. On this bottom slide, you can see the percent contribution of organics to CCN. That means the difference over this one. And we can see areas where we have more than 100% contribution of organics. And it's really almost 100%, not more than 100%, almost 100% contribution. And globally is about 70%. And it's not the only model, our model, that gives this result. There are also other studies by the University of Leeds who came to about the same conclusion. So the other test we have done is what I mentioned to you earlier is that might be that the size distribution of the emissions that matters. So what we have done is we use the same emissions of carbonaceous aerosols, black carbon and organic carbon, but we consider larger particles. Same mass emissions, larger particles means fewer particles, but larger. So this makes, this is the CCN base case, and this is the change in N3. That means all particles above 3 nanometers. So you see a very dramatic change, about 70% on global. We have 70% less particles in our modeling system. If we inject larger particles, we have larger emissions of, larger particle emissions of combustion aerosol. And the change on CCN, you can see it here. So we have changes around 50% in these regions and smaller elsewhere, but a total of 10%. It's important. It's a 10% just uncertainty because you have a little bit larger particles than in the base case. So that's another reason of uncertainty. And this is a very messy figure. I wouldn't like to put it on, but it's really good. So it's not my figure. This is a contributor to the paper from the Leeds University. It's the Leeds University. They have a kind of they have this HAD-GEM UK model in which they are able to do how they call it perturb parameter ensemble simulation. So they have done something thousands. 260,000, I think, simulations perturbing one parameter into their model. They have an emulator system with which they can do it. We can discuss that later if you want. So they have been able to evaluate the uncertainties at each of those stations that we looked at, and to what they are due. The uncertainties in the CCN. So they looked at different parameters, and I marked here the most important ones for us. Organic aerosol hygroscopicity. So this is the color to help you because I had a hard time to read it also. This is the color, and you see at Finocallia, for instance, summertime, we have this contribution. Melpitz in Europe, Jungfraujoch, Hutiala, Wawichl and Noto Peninsula. So here also and there, but so you see some places where you have a significant contribution to the uncertainty in the CCN calculation related to the hygroscopicity of the organic aerosol, if it's very hygroscopic or less. And this is very hard to tackle, this problem, because you have thousands of organic compounds and they can span the whole range of hygroscopicity. I don't know how we'll handle that. We're going, at least for the moment, we have some mean numbers, but the variability and the mean numbers do not go together. So the second part is the biogenic secondary organic aerosol. Secondary organic aerosol coming from biogenic volatile organics. And this is this color, this blue light. You can see it here in Hutiala, lots of it. In Jungfraujoch here, in Melpitz, you can see it also in Finocallia. And here in Puy-du-Dôme, it's in the middle of France, this one. So you can see significant contribution during summertime from organic aerosol, hygroscopicity or secondary organic aerosol. And then what remains this nice green here, and we wonder what it is. And this green here is dry deposition of aerosols. It's very uncertain also. So those are the three major uncertainties that have been identified this way. So that was our contribution. So now the question is how the CCN uncertainty reflects in the cloud droplet number concentration calculations, because we have not done it to know what is CCN. We have done it to see also how far we can trust the clouds formation in the model. So what we have done for that is we took the model CCN spectra, that means the CCN as model for different supersaturation ratios, supersaturations, and it's CCN as a function of supersaturation. We took the observed CCN spectra from the stations where they had enough data to be able to make this function. In reality, it has been a fit to the model data and a fit to the observations to get a continuous spectra. And then this has been used in the program that Nennes and Seifel published in 2003, the approach. And accounting for this spectra of CCN, the temperature at the base of the cloud, and also accounting for the updraft velocity in the cloud, then you can model you can calculate the CDNC, which is in reality it's the amount of CCNs that activate under these specific conditions. So, and we use two different updraft velocities, one small one that is typical for stratiform clouds, and the other that is double and is typical of cumulus clouds. Messy figure again, but we'll make it simple. This is all the results. So, what do you see here? First, at the top here, you see the cloud droplet number for the different stations as calculated. We see it here as ND droplet. It's the CDNC I was talking before. Then we see the maximum supersaturation at which the CCNs activate. And then we see here the sensitivity of the cloud droplet number to the aerosol number at the different stations, and at the bottom is the sensitivity of the cloud droplet number to the updraft velocity. The one is the aerosol, the other is dynamics. And we have two different colors again. The red is for a small, the smallest updraft velocity, and the green is for the high updraft velocity. Okay, let's see how we handle that now. We put a line here to check on something. So first you see that the cloud droplet number concentration is highest for the high updraft velocity. Okay, those have been calculated based, and the red and the green line have been calculated based on the same CCN spectra. The difference is the updraft velocity. So faster it goes up, more easy is to make cloud droplets. You have condensation, and you have increase to cloud droplet size. So you have, so we see the model, the highest updraft velocity leads to the highest number of cloud droplets, and with the spots we see what is the result from using the CCN spectra from the observations. So we have the same middle tool to calculate it, but the one is based on model CCN and the other is based on observed CCN. So we see that we have an underestimate. We have underestimate in the CCN. It's normal to have an underestimate in the CDNC. But it's not that simple, because if we look at the supersaturation, the maximum supersaturation, then we see an opposite trend. More CCN you have and more CDNC you produce, the maximum supersaturation goes down, because somehow let me see if I say that well. There's a competition for the water availability. So if you have a lot of them, then the water availability is the one making that you have a limited factor. So you have a minimum and maximum supersaturation. And this also corresponds to the case where the sensitivity of, you have many particles, the sensitivity of droplets to the aerosol number is low. And that means a lot of CCN, high cloud droplet concentration, low supersaturation, maximum supersaturation, low sensitivity to the aerosols. And then high sensitivity to the updraft velocity, because this is what will bring you the water in reality around. So we see here, let me see, do we see here? Yes. We see here an anti-correlation in the sensitivities of cloud droplet concentration to the aerosol number and to the vertical velocity, the updraft velocity. And this is what somehow, I say buffer, but it's not buffer, but this is what limits the system. So this on this slide we can clearly see that how what we have done. We had all those points here. So we just done a mean for each station, and we put the standard deviation on it. So on this one you have the multimodal mean for number cloud droplets, and the derived cloud droplet concentration from the observations. For the two updraft velocities, green is the highest one and red is the lowest one. And we see that more or less we're getting there. I mean, the models are able, are doing much better than we thought to simulate the what we call derived from observation cloud droplet number concentration. If we look now the CCN we do not have it on in the aerial slide, but you have it in some others before. So we have CCN at supersaturation of 0.2% and CCN at the highest supersaturation measured at the station, specific station. So you can see that there is an underestimate. And this underestimate does not have anything to do with this one. I mean, we are worse in CCN than we are in cloud droplet number concentration. And that's good. I'm happy about it. We can do something. but and why this happens is, as we explained before, is because those who underestimate the CCN, they overestimate the maximum supersaturation ratio. So the balance of the two of them will lead finally to a CDNC. So the number of CCN at the prescribed supersaturation cannot be really the indicator of the CDNC, because there's a lot of dynamics that are affecting, and those dynamics are specific for each site. So I think I'm getting close over time always. So the conclusions of this work is that, okay, we have done the first comparison of models with a kind of experimentally derived CDNC. And the spread of the models in cloud droplet concentration calculations is smaller than the spread in the CCN and in the aerosol number concentration of other sizes. So the variability in the aerosol number and in the omega, the updraft velocity, both of them, the sensitivity that means, is the one that is controlling finally the cloud droplet number concentration. So we need both aerosols and dynamics. And okay, those are banal things. There's an underestimate of different things. Organic aerosol is important contributor to CCN, but also to the summertime uncertainty in the CCN. It's not only that it adds to the CCN, but also is the uncertain point that we have to correct together with the dry deposition. And the other point that we found out is that the size distribution of the primary emissions of carbonaceous, but I imagine we can do it for others also, and the new particle formation and growth are the processes that have to be also improved in the models. So all this work will be soon, I hope, next week, submitted to atmospheric chemistry and physics. I'm not the only one doing that, although I started it in Bacchus, but there's a bunch of people from all around the globe. It started like a Bacchus project, but it became an IROCOM international project, are in there. And I would like to thank you for your attention. Ευχαριστώ.